carrying the current. So this type of magnetic field we got. After that, we have discussed a current carrying loop will behave as a magnet. Okay. We did some of the questions also. So now we will discuss the electromagnet. So first see what is the electromagnet. This is the electromagnet. So what is in the electromagnet? What are the components of the electromagnet? This is a soft iron core. Hmm? This is a soft iron core in cylindrical shape is this. Hmm? In the cylindrical shape. So what you did, you have bonded the wire like this. Suppose this is a soft iron core and I have bonded the wire, hmm, insulated wire on this, and that wire I have connected somehow through the battery. And when I will open or I will close the switch, current will start flowing in this wire. Current will start flowing in this wire. You can take the wire of aluminium and wire of copper also. So basically here we have taken the wire of copper because copper is having the high conductivity, as compared to aluminium. So as compared to aluminium. So what will happen? So this is the battery. This is the battery. This is the switch. Battery, switch, soft iron core, and this is the wire bounded on this soft iron core. So if you will close this switch, so in this circuit the current will start flow, means the current will start flowing in this wire. And what will happen? I told you that a current carrying wire produces the magnetic field. So basically this wire will produces the magnetic field, and it will become an it will behave as a magnet. And why we have used the soft iron core? Electromagnets are not the permanent magnet. Electromagnets are not the permanent magnet. Just a minute. I have a call. Okay. So electromagnets are not the permanent magnet. Like I told you that about the bar magnet. We did the bar magnet. So the bar typical magnet is a permanent magnet. Hmm? That was the permanent magnet. But the electromagnet is not a permanent magnet. The magnetism of electromagnet will remain until the current is flowing in this wire. When you will switch off the current, when you will switch off the current, when you will switch off the current, it will loses the magnetism. Why? The reason is that the reason is that due to what there is a magnetic field. Due to what? A magnet is something which creates a magnetic field. A magnetic something which creates a magnetic field. So this is creating the magnetic field by because of the current flowing in this wire. Because of the current flowing in this wire. And when you will open this switch, current flowing will stop and magnetic field will discontinue. It will not produce, this wire will not produce the magnetic field. So that is why this uh, uh, electromagnet is not a permanent magnet. Okay. Okay. Why we are using the soft iron core? Because soft iron core will magnetize because of the magnetic field produced by this wire. This soft iron core will behave as a magnet also. It will magnetize. Magnetize means it will behave as a magnet. But this soft iron core is having the property, when you will switch off the current, this soft iron core suddenly loses the magnetism. Loses the magnetism. So that is why we are using the soft iron core, because we want the temporary magnet. If we will use steel is not a steel we cannot use as a soft iron as a core. in this case. Why? Because when you will switch off the current, okay, so in that case what will happen in case of the steel? Now you have switched off the current, but this time also in steel there will be some magnetism left. Okay, but in case of the soft iron core, when the current will become zero, after fraction of time, it will loses the magnetism. So basically, an electromagnet produces magnetic field by using current. Okay, these are temporary magnets and works on magnetic effect of current. Magnetic effect of current means with the help of current we can produce the magnetic field. Okay. Now example of the electromagnet is solenoid. Solenoid with soft iron core. So we will discuss the solenoid. What is solenoid? We will discuss. That is our next topic, the solenoid. Okay. Okay. Hamna and all. So this is about the electromagnet. Once again, I am telling this is a soft iron core. A wire is wounded on this. That is copper wire, and this wire is connected with a battery. And here is a key. When you will close this key, current will start flowing in this wire, and due to that current flowing in the wire, magnetic field will produce. And due to that magnetic field, this soft iron core will magnetize and it will behave as a magnet. Means it can attract the iron pieces. When you will switch off the current, then magnetic field will become zero, and also the soft iron core will loses the magnetism. Okay. So now we will discuss the solenoid. Magnetic field pattern due to the solenoid. So solenoid is this same thing we did. No, this is a solenoid. This is a solenoid. So basically solenoid, you can say that if you have taken a wire like this, okay, we will use this figure in last. See this figure first. So in this figure, you can see this is the wire only. No core is there. So this is the wire wounded like this, spiral form. So and current is flowing in the wire. So due to that, what is happening? This is the magnetic field pattern. This is the magnetic field pattern. You can see in the in this coil, in the middle of this coil, the magnetic field lines are nearly straight lines. So in this region, the magnetic field value is constant value. Is constant value. Constant value means magnetic field is not changing here from here to here to here to here. The magnetic field is constant. Okay. So this is the magnetic field pattern due to a solenoid. And what is a solenoid? Simply a solenoid is just you have wounded the wire in the helical form and current is flowing in that wire. This is a solenoid basically. This. Now we have seen another pattern of magnetic field. Basically, this is the magnetic field pattern due to a solenoid. This is a solenoid. This is a solenoid. And these are the magnetic field lines. These are the magnetic field lines. And this is the current flowing. So due to the current, there will be the magnetic field. When you will draw that magnetic field, it will become the magnetic field line. And here, in between, the magnetic field is constant. Uniform, you can say magnetic field. Uniform means throughout the distance from here to here in this region, the magnetic field is not changing. Uniform magnetic field. uniform magnetic field. Now, see the difference between the magnetic field pattern due to a bar magnet. So this is a bar magnet. Hmm? So these are the magnetic field lines due to a bar magnet, like this, like this, like this, and like this. So basically, it is looking something similar to the bar magnet. Okay, this is a bar magnet. So these are the magnetic field line due to a bar magnet, and these are the magnetic field line due to a solenoid. Something similar here. So basically, this solenoid will become the electromagnet when you will want this wire on a particular core. Okay, this is this solenoid na. Basically, solenoid and electromagnet are same thing. Okay, there is no difference. The little difference is that when you say the electromagnet means you are using the iron core, soft iron core. So this is the soft iron core. Soft iron core is there, and this wire is wounded. This is the copper wire, you can say. When they are saying draw the magnetic field line due to an electromagnet, then also you will draw the magnetic field line due to a solenoid, like this. So basically, this is a solenoid with soft iron core inserted, and this is a only simple solenoid. No iron core is inside this solenoid. So the magnetic field increases. Okay, remember one thing, when we insert this soft iron core na, so what happens, the magnetic field strength due to the solenoid will increases. Okay, so a solenoid is a long coil, this is a coil na, long coil containing large number of turns of insulated copper wire, large number of turns of insulated copper wire. Okay, this is a copper wire. You can say this wire is of copper wire. A solenoid is a long coil containing large number of turns of insulated copper wire, and this copper wire is insulated. Okay, plastic covering will be there on the copper wire. Okay, after that, magnetic field produced by a current carrying solenoid. So basically, this is a current carrying solenoid. Magnetic field produced by a current carrying solenoid is almost same as that of bar magnet. So you can see this is the magnetic field pattern due to a bar magnet, and this is the magnetic field pattern due to a solenoid. So you can compare, almost you will find that same magnetic field pattern is there, almost same, not exactly same, almost same. So magnetic field lines inside solenoids are in the form of parallel straight lines. So you can see here, this is a solenoid, and inside this solenoid, the magnetic field lines are parallel straight lines. So parallel straight lines means that the magnetic field is a uniform. From here to here, the magnetic field is same because of these parallel straight lines. Whenever you are drawing the parallel straight magnetic field lines, like this, like this, like this, it means that the magnetic field in this region is uniform. Okay. Which means the strength of the magnetic field inside solenoid at every point is same. Okay, after that, now strength of magnetic field produced by the solenoid carrying current. Basically, this topic you will study in detail in your 12th class chapter magnetic effect of current. There will be also a chapter magnetic effect of current. There in detail you will study, and that formula is V is equal to mu naught Ni. Okay, so that is not in your syllabus. Okay, so basic things I am telling you about that. So strength of the magnetic field produced by the solenoid carrying current depends upon, okay, depends on number one is, remember what I am saying, strength of magnetic field is depending upon number one, number of turns in the solenoid. More will be the number of turns in the solenoid, more will be the strength of the magnetic field. Magnitude of the electric current, more will be the current flowing in the solenoid, more will be the magnetic field. Okay. Nature of the core material used. Core material used means this is a simple solenoid. You will insert a core. Suppose this core you have inserted. So this diagram, after this diagram becomes this after inserting the core. Okay. So I am just what I am doing now. So I am just taking this diagram from here. So basically, this becomes the, this is a simple solenoid and this is a solenoid with core. Solenoid with soft iron core. So this is a simple solenoid and after inserting the core, the solenoid will become like this. Okay. So I'm drawing it here. After inserting core. So this core you have inserted. Earlier there is only wire like this. This wire is like this. This wire is shown here. When you will insert the core inside it, it will be looking like this. And due to that, the magnetic field strength will change. It will increase basically. Okay. Now magnetic field strength will depend upon the material of the core also. If you will use the core of steel, then the magnetic field strength due to the solenoid will be different. If you are using soft iron core is best. And soft iron due to the soft iron core, the magnetic field will be different. So here is nature of the core material used. So basically the magnetic field produced or magnetic field strength produced due to the solenoid is depending upon the nature of the material, means of which material you are using the soft or of which material you are using the core for the solenoid. Okay, so the use of the soft iron rod as cores, this is basically what? This is a rod of soft iron, rod of soft iron as core. So this is a rod of soft iron. So the use of soft iron rod as core increases the strength of magnetic. Understanding Aman, Hamna, Martin, Sarah.
Yes, sir.
Yes, sir.
Okay, so so this is the question. The magnetic field in a given region is uniform. Draw the diagram to represent it. Uniform magnetic means uniform magnetic field line means parallel straight lines like this. These are the magnetic field lines. Okay, so parallel, straight lines. So magnetic field, the magnetic field in a given region is uniform. Means in a region, magnetic field is uniform. I told you what is the meaning of uniform. Means here, everywhere the value of magnetic field, strength of magnetic field is same. So how to represent that magnetic field with the magnetic field line? So magnetic field line of a uniform magnetic field will be parallel straight line. So this is the diagram you can use, or either you can use this. Okay, so these are the magnetic field lines. Okay, so parallel straight line. So this is your answer. You can see these are the parallel straight lines. So basically, where we got the uniform magnetic field, just I have given one example. Here, these are the parallel straight line, and these parallel straight lines are inside the solenoid. So inside the solenoid, we are getting the uniform magnetic field. So you can relate this also. Another question. What is the another question? So now another question is, what is an electromagnet? I have written the definition. Describe the construction and working of the electromagnet with the help of a label diagram. So you can use these notes. This is the you will draw this diagram
Do we
and you will
write or do we take picture? Do we write or take picture?
This time also you have to take the pictures.
Okay, sir.
Okay. So what you will do now? I'm talking about the exam. Means in exam, they are asking you what is the electromagnet and draw the diagram. So you will write an electromagnet produces the magnetic field by using the current. Okay. And these electromagnets are temporary magnets and works on the magnetic effect of current. And you can give one example also, and you can draw this diagram there. And okay, so this question is solved. Is it or not, Sarah? And Hamna, Martin, Aman.
Yes, sir.
So what is an electromagnet? Okay. And describe the construction and working of the electromagnet with the help of the label diagram. Okay. So construction, you can do construction, means this diagram you can draw. This diagram. What is the working? Working is very simple. When you will switch on the current will flow in this wire, and whenever the current is flowing in this wire, magnetic field will produce. Okay. This is the working. Okay, another. Explain why electromagnet is called temporary magnet. So this is also very easy, because when you will switch off the current, the magnetic field due to the electromagnet will become zero. That is why it is a temporary magnet. I told you. Explain why the core of electromagnet should be of soft iron and not of steel. This answer also I told you. What is the reason that why we are using the soft iron core in case of the solenoid or in case of the electromagnet? Why? Because soft iron core loses the magnetism easily, gains or loses the magnetism easily. But in case of the steel, once it gains the magnetism, it will take time to lose the magnetism for steel. That is why steel cannot use to make the temporary magnet. Okay. So state the factors on which the strength of the electromagnet depends. How does it depends on these factors? I told you that on which factors you can see here. Number one, number of turns. Okay. Okay. Current flowing and material of the core used. Okay. So number of strength of the magnetic field depends upon the number of turns in the solenoid or in the electromagnet. Solenoid is also electromagnet. Okay. Magnitude of the electric current flowing in the solenoid or electromagnet. Nature of the core material used. Okay. And how it is depending is when you will increase the number of turns, When you will increase the number of turns, the magnetic field strength will increase. When you will increase the electric current, the magnetic field will increase. Okay. When you will use the material as soft iron core, again the magnetic field will increase. So write some important uses of electromagnets. So one use I am telling, electromagnets are used in for the medical purposes. Okay, suppose some of the iron goes inside your body. So to remove that iron, doctors use the electromagnet, and electromagnets are also used in the transformers. Other uses you can write. Okay. After that, uh, we will discuss the difference between the bar magnet and the electromagnet. Bar magnet and the electromagnet. So first, what is bar magnet? So bar magnet is a permanent magnet, or electromagnet is a temporary magnet. Okay, so its magnetism is only for the duration of the current passing through it. Hmm? So magnetism of an electromagnet can be switched on or switched off as desired. As desired means when you will switch on the current, it will behave as a magnet. I am talking about the electromagnet. Electromagnet will behave as a magnet when you will switch on the current. When you will switch off the current, it will not behave as a magnet. So it is a temporary magnet, it is a permanent magnet. So now bar magnet. So a permanent magnet produces a comparatively weak force of attraction. So basically they want to say that the magnetic field produced by the permanent magnet is weak. That is why now magnetic field is weak. That is why the magnetic force due to that magnetic field will be weak. Okay, so basically second point is a permanent magnet produces a comparatively weak force of attraction. An electromagnet can produce very strong magnetic force. So as compared to the bar magnet, electromagnet produces the electromagnet produces very strong magnetic force. Okay. The strength of the permanent magnet cannot be changed. You cannot change the strength of the permanent magnet, but by increasing the current, by increasing the number of turns, by changing the material of the core, you can change the strength of the magnetic field by the electromagnet. So the strength of electromagnet can be changed by changing the number of turns in its coil, or by changing the current passing through it, or by changing the core material. The north-south polarity of a permanent magnet is fixed and cannot be changed. So obviously in case of the bar magnet, you cannot change the polarity north-south pole. But in case of the electromagnet, if you will change the direction of the current, polarity will change. So the polarity of the electromagnet can be changed by changing the direction of the current in its coil. Okay, so one by one you should take these screenshots. Then we will discuss the force on a current carrying conductor in magnetic field. Done? Taken the screenshot?
Yes, sir.
Others?
Yeah,
Just wait. Okay, so now you can take the screenshot. Okay, I am removing this. Okay, this diagram. So just wait for a second. So basically now it's fine to take the screenshot.
Done, sir.
Okay. Martin and Aman completed, and Hamna. Scroll down. Martin.
Yes, sir.
Okay. So now you can take the screenshot. This one.
That answer.
Okay. Please take this also. This screenshot also for a bar magnet. We already did this, but you should take this for comparison.
That would, sir.
Okay. Sarah, done?
Yes, sir.
Okay, very good. So now this is the theory part. You should take the screenshot of this also.
Done, sir.
Okay. Okay, please take this one.
That answer.
Okay. Now you can take the screenshot of this also. Done? Sarah and Hamna and
Yes,
Aman
sir.
and Martin. Okay. Okay, if you want, then you can take the screenshot of these questions also.
So can you scroll up? Can you scroll?
Okay, okay. Okay.
Yeah, next.
Okay, so you can take the screenshot of this.
Done, sir.
Yeah, that answer.
Okay, so uh, now difference between the, okay, you can take the screenshot of this also.
Done, sir.
Done, Martin?
Yes.
Aman? Okay.
Yes.
Now we will discuss the force on a current carrying wire. Means if suppose this is a current carrying wire and around this wire there is a magnetic field. Imagine there is a magnetic field around this wire, and if in this wire there is a current, definitely there will be a magnetic force on this wire. If suppose this wire is like this in this direction and magnetic field is in this direction, and this and direction of the current is in this direction, so so there will be a magnetic force. There will be a magnetic force on the wire. Okay. Wherever there is a current carrying wire placed in the magnetic field, it experiences a magnetic force. It experiences a magnetic force. So now let's say this is one of the examples. Basically, what is this? This is a magnet. Now this is north pole, this is south pole magnet, and this is a conductor. Whenever I am saying wire, it means conductor. So a conductor is placed. Okay. So what you will do now? When there is a current in this conductor, so this conductor will push upward. It is seen that this this conductor is pushed upward. So, but when the current will become zero, again it will occupy the same position. When again you will switch on the current, it will push again upward. Now, why this is happening? It is happening due to that, because if this is a current carrying conductor and this current carrying conductor is placed in the magnetic field, and where is the magnetic field? Due to the magnet. Due to this magnet, there is a magnetic field, and this is a current carrying conductor. Means current carrying conductor is placed in the magnetic field, and it is pushed upward. Means it experiences a force. Something is pushed upward means that thing is experiencing some force now. So in this photograph, we can see the piece of aluminum foil that has been fixed between the poles of the strong magnet. When a current is passed through the foil, it is pushed upward away from the magnet. It happens due to the repulsion between the two magnetic fields, one from the magnet and one from the current. Basically, we know that the current carrying conductor also produces the magnetic field, and there is a magnetic field due to the magnet also. So due to the magnetic field of both, they both will repel, and that is why this conductor is going upward. Or this indirectly we can say that current carrying conductor experiences a magnetic force in the presence of magnetic field. Okay, so you can write now, when a current carrying conductor placed in magnetic field, when a current carrying conductor when a current carrying conductor when a current carrying conductor placed in magnetic field placed in magnetic field, magnetic force is exerted on the conductor. A magnetic force is exerted on the conductor. A magnetic force is exerted on the conductor which can make it move. Means due to that the conductor can move. So due to that the conductor can move. Due to that the conductor can move. The conductor can move. Okay, you can see in this example, on this conductor there is a current, and this conductor is moving in the magnetic field. Means this conductor is experiences some force. Now, what is the direction of the force? Direction of the magnetic force. Force is a vector quantity, so it will have the direction. So direction of the magnetic force. Direction of magnetic force. Number one is perpendicular to is perpendicular to the direction of current, perpendicular to direction of current flowing in conductor, current in conductor, you can say. Number second, this magnetic force is also perpendicular, perpendicular means 90 degree, perpendicular to the direction of magnetic field, to the direction of magnetic field, to the direction of magnetic field. Okay, there is one rule to find the direction of the magnetic force. That is, you can find with the help of that rule either the direction of magnetic field, either the direction of the current, and either the direction of the magnetic force. So generally we say with that rule we can find the direction of the magnetic force. So that rule is Fleming's left hand rule. Fleming's left hand rule. So what is the Fleming's left hand rule? So adjust your left hand like this. So this is thumb. This is forefinger. This is the middle finger. Thumb, forefinger, middle finger. So adjust your left hand in this way. All the three fingers should be perpendicular. All the three fingers should be perpendicular. Okay. Now, if this forefinger is representing the magnetic field, this you can write on this finger magnetic field. Okay. So here is the magnetic field. This finger is representing the direction of the magnetic field, and this finger, middle finger, is representing the direction of the current. So write it. I am not saying write it, just try to imagine. It is representing the current. So the direction of thumb will give you the direction of the magnetic force on the conductor. Direction of thumb will give you the direction of the magnetic force on the conductor. So we can write it first, then we will solve one question, then you will understand it properly. So adjust your left hand in such a way you can write it in such a way that the forefinger is representing the direction of the magnetic field, middle finger is representing the direction of the current, then the thumb will represent the direction of the force or direction of the motion of the conductor. So adjust your left hand in such a way that the forefinger points in the direction of magnetic field, points in the direction of points in the direction of magnetic field, points in the direction of magnetic field, points in the direction of magnetic field, and or you can say middle finger points the direction of, or you can say center finger points in the direction of current flowing in the conductor, in the direction of current. Then the direction of thumb, the direction of thumb means the direction in which the thumb is pointing. Either thumb will be pointing in this direction, in this direction, in this direction, in this direction. Then the direction of thumb will give you the direction of, will give you the direction of magnetic force acting on the conductor. Direction of magnetic force acting on the conductor. Okay, so adjust your left hand in such a way, adjust your left hand in such a way that your forefinger is representing the direction of the magnetic field, your middle finger or center finger is representing the direction of or pointing in the direction of magnetic field, then your thumb will give you the direction of the magnetic force. So basically thumb will represent force, this forefinger will represent magnetic field, and center finger will represent direction of current flowing in the conductor. So adjust your left hand in such a way that the forefinger points in the direction of the magnetic field, forefinger magnetic field, center finger current, and thumb force, or you can say magnetic. Okay, so now this is the question. This is the question. A stream of positively charged particle, a stream of positively charged particle, alpha particle. Alpha particles are basically the positively charged particles moving towards west direction, is deflected towards north by magnetic field. The direction of the magnetic field is, so we have to find the direction of magnetic field. So this is east direction, this is the west direction, this is the north, and this is south. Okay, so what they are saying, a stream of positively charged particle moving towards west means positively charged particles are moving in this direction, and I told you that the motion or the direction of the motion of the positive charge, this is charge, is the direction of the current. So current will be towards the west direction. So in this direction there will be the current. I means current. And the direction and after that they are saying that deflected towards north means the particles going in the west direction, these are deflected towards north, means the force, magnetic force on the particles will be towards north. This is the magnetic force. So what will be the direction of the magnetic field? What will be the direction of the magnetic field? So magnetic force is perpendicular to the current and also perpendicular to the magnetic field. So here magnetic force is perpendicular to the current. Now this magnetic force will perpendicular to the magnetic field. Now how it will perpendicular to the magnetic field? Either the magnetic field will be upward or either it will be downward. So two options can be removed. upward or downward. And for finding that, we will use the left hand rule. So point your uh, forefinger toward the basic point your thumb toward the force. Okay, point your thumb toward the force and point your middle finger toward the current. Okay, point your middle finger toward the current. Okay, so basically this is the direction of the force toward the north, and this is the direction of the current, like this. Okay, it will be like this. Try to do this. Okay, so force is towards the north direction. Okay, and current should be in this direction. Okay, like this. Okay, it will be like this. Hmm? When you will do on the paper, now draw it on the paper, then you will understand it properly, like this. Okay, in a screen, I don't know whether you are getting it or not. Like this. F, magnetic field, and current. Okay, so you have to do like this, okay, like this, like this. Hmm? So basically this is representing the current direction, this is representing the force direction, and this finger is representing the magnetic field direction. So magnetic field direction will be upward, like this. Okay, like this. Understanding or not? Force, force,
Yes.
force, current, thumb force, current, magnetic field. Draw on your paper, then you will understand it properly. So basically the answer will be in the upward direction. Why? By using Fleming's left hand rule. Okay, so you can write which rule we are using. Okay, after that, these topics, homework you can do with the help of the NCRT, and these are simple topics. Dangers of electricity. Okay, give me 1 minute, I'm just coming. Okay, so dangers of electricity. So we know that dangers are also there apart from the advantages. Okay, so one by one we will read it. If a person happens to touch the live electric wire, he gets a severe electric shock. So in domestic wiring, there is one live wire, okay, and there is one neutral wire, and there is one earthed wire. So if you will touch the live electric wire, you will get the electric shock, okay, and after that you can read it. Short circuiting due to damaged wiring. Suppose there is a place where wiring is not that in a proper manner. So there will be the short circuiting, and due to short circuiting, there will be the large amount of current. And due to large amount of current, there will be large amount of heating effect of current. And due to that, fire can be there in the building. Another, the defects in the household wiring, like loose connection, defective switches, sockets, and plug, can cause sparking in the lead to fire. You have seen, maybe you have seen or not, there are sparkings also due to some malfunctioning or due to some poor connections. Okay, and due to that there will be sparking, we can see, and we can get the electric shock by that also. Okay, and that sparking can also burn sometimes, can convert into the fire. Okay, after that we have the precautions. So precautions, uh, so first you should take the screenshot of these all fast. Okay, fast you should take the screenshot, all of you. Done?
Yes, sir.
Yeah.
Okay. Okay. So please write down this fast. Please take the screenshot.
Done, sir.
Okay. And Amna and Martin and Sarah. Martin done?
Yeah, done, sir.
Okay. 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 So you can write here the heading. Just a minute. Fleming's which rule? Left hand root, not right hand root. Right hand root rule is deleted this time. So Fleming was scientist. Left hand rule. Okay. Now you can. And why we are using Fleming left hand rule? To find the direction of the magnetic force, or it can also be helpful in finding the direction of the magnetic field or current. Okay, so please take this screenshot fast.
Done, sir.
Then okay, now you should write take the screenshot of this statement of Fleming's left hand rule. Done? Sarah and
Yeah, okay, I took, sir.
Sarah done?
Yes, sir.
Okay. Now please take this screenshot. But what we are using here? We are using Fleming's left hand rule. Okay.
Yes,
Using
sir.
just a minute, I will tell you when to take the screenshot shot using Fleming's left hand rule. Okay, so now you can take a screenshot of this also. And F is representing the magnetic force, I is representing the current.
Yeah, took, sir.
Okay, so please do this by yourself and you can take the screenshot of this also. Done?
Yes, sir.
Okay, so please take the screenshot of this also.
Done, sir.
Done? Okay. Martin and Hamna.
Yeah, I took, sir.
Okay, so now you can take the screenshot of this. So precautions, it's also very easy. So to avoid the hazards like electric shocks or electric fires, I told you, no, there can be the electric shock, there can be the electric firing. We should observe the following precaution in the use of electricity. Number one, if a person accidentally touches a live electric wire or an electric fire starts in the house, the main switch should be turned off at once so as to cut off the electricity supply. This will prevent in fire from spreading. So for example, suppose I am sitting here, somehow here is a socket. In this socket, due to this socket, there is the electric is sparking, and due to that there is firing, and that firing is why that firing or that sparking is happening is due to the electricity. So what I will do to prevent that situation when it will arise, I will just open the or okay, cut off the power from the main switch. There is one main switch na in the home. So we will try to cut off the electric power from there, and when electric power will cut from there, current here will become zero. And so the person who happens to touch the live electric wire should be provided an insulated support of the wood, plastic or rubber. This is very easy. For example, if someone is touching the wire, so he should after that the person who happens to touch the live electric wire should be provided an insulated support of wood, plastic or rubber. We should never try to pull away the person who is in contact with the live wire, otherwise we will also get a shock. So basically this is also very simple. Suppose if you want, if not you want to, somehow there are the, if there are chances that if there is something important and you have to touch the live wire, other okay, but on live wire also there are insulations. So if you are touching, so you should have proper gloves, and that gloves should be of not non-conducting material. Okay, because it can be possible that you are touching the live wire and insulation of live wire, that live wire is weak, so you will get a shock if you will not wear the gloves of wood or rubber or some non-conducting material. One more thing, for example, suppose I am touching this device, and this device, due to this device, do you know in human body also the current can flow? Yeah, human body also the current can flow. Suppose something, so suppose I touch this, okay, so what will happen? Due to that, there will be the current in my body. Okay, so if any other person will is touching me, na, so that person will also experience the electric shock. Okay, so they want to say this, I think we should never try to pull away the person who is in contact with the live wire, otherwise we will also get shock. All the electrical appliances like electric iron, cooler, refrigerator, etc. should be given earth connection to serve ourselves from risk of electric shocks. Even if the earth connection is there, we should avoid touching the metal body of the electrical appliances when it is on. Basically, now what happens, suppose uh, here is the wire, this is the wire, and I am touching this wire. So what will happen? From this wire, the current will flow through my body, and that current will flow through my body, and through my body, the current, that current will goes to the earth. Means the circuit will be completed. So what we should do now? We should use the insulations. Either we can use the insulation or we can use the earthing connection. Okay, if you will use the earthing connection, means what will happen? The potential of this wire, okay, that I am touching, means one of the earthed wire is connected to the earth. So basically, what will happen? Earth is at zero potential. So all the charge will flow from here to here. Okay, and when you will touch this product, you will not get the shock. Okay, So basically, this thing they are saying all the electrical appliances like electric iron, cooler, and refrigerator should be given earth connection. Should be given earth connection to save ourselves from risk of electric shock. Even if the earth connection is there, we should avoid touching the metal body of electric appliances when it is on. This earthing, now you will study when I have given the homework. Now in this you will get this. Okay, domestic electric circuit and electric fuse. So there will be a concept of the earthing also. So in this that will be covered. Then you can understand this point in a more better way. Okay.
Yes, sir.
Okay, so this chapter is finished now, and with that your syllabus is also finished. Okay, so when will be your the exam? First exam on 22,
20.
on 20.
Yeah.
Okay, so I think this is our last class. After that, you will prepare for your exam, I think. And
Yes, sir.
Martin and Sarah and Hamna, all the best to all of you. And uh, revise all the things properly. Okay, whatever the best you can do, try to do that. And one more thing, whenever you are solving any problem in exam, whenever you are solving any problem in exam, and also when you are practicing or when you are revising, so always try to think of time also. Within time, we should solve the problem. Okay, there should be a time constraint also. Okay, and one more thing, read the questions or problems properly, and after that collect what is the data given, and after that relate with that data with your knowledge, and then you should solve that. Okay, do not be in hurry, do not solve any question. Okay, because if you know the question, then you can 100% solve it. Okay, and don't take stress, and do the revision properly. Okay, and now give 100% focus to your studies now, because time is less. And to all of you, all the best. Okay, and I have tried my best, whatever the knowledge I have tried to give you. Okay, in whatever the manners. And okay, so all the best, all of you.
Thank you,
Do
sir.
your best. Okay.
Thank you, sir.
Okay. Okay, Martin.
Okay, sir. Thank you.
Okay. Okay, Amna.